The generator is, I think, the most interesting part of a GAN because its job is to really learn something about the underlying structure of training data. In the case of our house numbers, the generator should learn what shape and color features make up these images, and then it will learn to imagine in that space, combining these features in new ways to create realistic generated images. As before, the input to the generator is a random vector z, usually with something around 100 values. The output of the generator needs to be an image that can be sent to the discriminator. That means we need to upsample the vector z until we get to an image that is 32 by 32 by 3, the same shape as our training images. This may remind you of the autoencoder lesson, in which we upsampled a compressed input using nearest neighbor interpolation or transposed convolutional layers. For this generator, we're going to use what was found successful in the original DCGAN model, transposed convolutions. To review, transposed convolutional layers are similar to the convolutions you know and love, but with the opposite effect. With convolutional layers, you typically go from shallow and wide inputs to deep and narrow outputs. But with transposed convolutional layers, you go from narrow and deep inputs, like vectors, to wide and flat outputs, like images. This is a diagram of the DCGAN generator, showing the transposed convolutions, progressively upsampling the layers. Consider using a layer with a stride of 2. When you move the convolutional kernel 1 pixel in the input layer, the kernel will move 2 pixels in the output layer. So it's moving 2 pixels in the output layer for every 1 in the input layer. And the output layer size depends on the stride. With a stride of 2, the transposed convolutional layer output will be twice the width and height of the input layer. Now, the first step in the generator is to connect the input vector z to a fully connected layer. Then we'll reshape that fully connected layer to a 4x4 XY shape with some depth that we specify. Then we build a stack of larger layers by upsampling with transposed convolution. Each layer is doubled in XY size using strides of 2, so from 4 to 8 to 16 and then 32. Simultaneously, the depth is reduced as we move forward through these layers. The final layer, the output of the generator, is a 32 by 32 by 3 convolutional layer, which is exactly what we want as the size of our generated images. For the generator, the authors of this original GAN paper used ReLU activations and batch normalization on all hidden layers. The last layer is the only one that should not have batch normalization. Instead, we'll just be applying a tanh activation function to the outputs of the final layer. This will give us our desired output pixel values in a range from -1 to 1. So this completes our GAN architecture. We'll have 2 adversarial networks, and the training and optimization strategies will be the same as what you've seen before. Next up, you'll learn more about batch normalization. With batch normalization, you'll be able to create deeper networks for the GAN and get better results.